Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
It's just not a common conversation topic in the US, so I'm glad I'm here today. I don't know if it's common here, but here's a recent article from the Washington Post. Let me just pull up two quotes, you don't have to read it. Recent polling indicates that Doherty from the Sinn Féin party is leading the race, but Ireland's complicated, election system of proportional representation could upset the front runner and help the Fianna Fáil candidate running second in the polls to snatch victory. If you don't know too much about the proportional representation system, I just want to give, I won't go into detail, but I will give an example of a ballot from Ireland. Typically what you would do here is, instead of just ticking off the candidate that you like the best, you would go through one by one and rank the candidates from favorite to least favorite, something like this. Okay? And you might wonder, well, why would you have this more complicated election system of ranking instead of just ticking off your favorite candidate? There's a bunch of reasons, but one reason is that it encourages a different style of campaigning. So for example, you still want to be at the top of someone's ballot, but if you can't be at someone's first choice, you'd still like to be their second or third choice, right? And so as a result, it kind of discourages negative campaigning. You don't want to alienate a huge part of the population. It encourages people to vote for third parties, and it even encourages parties that have similar views to sometimes work together in a particular campaign. And it's not just Ireland that does this. It's Malta, Australia, Iceland. Even the Academy Awards are decided via proportional representation. It's very important stuff. It does have the con that it's not far, but it's somewhat more complex than plurality voting. Okay?
So you realize in 3 weeks we're voting on that?
I didn't know the timing was so soon. When I made these talks, it was a little while ago, but I'm glad it's very important here. So I will be talking about a real data set from 2002. This was data taken from the Meath region in Ireland, this green region. There were 14 candidates that year. There are two major parties in Ireland, Fianna Fáil and Fine Gael. Typically in the US, people have never heard of these, but I would expect maybe some of you would know more about this than even I would. There's a bunch of minor parties typically that play a somewhat important role in these elections. Despite the fact that rankings are somewhat more complicated, we still like to have a statistical analysis of this. For example, we might want to predict winners, identify voting blocks in the electorate. We might want to use this information to formulate better targeted campaign strategies. And if we could do all of these things, communicate the results, then I believe that we can engender a more informed, more effective democracy. Okay? Now, on the mathematical side, I'm going to talk about these elections as distributions, probability distributions over permutations. And here's just one of the examples of such a distribution. This row, for example, means that with probability 1/10, or 1/10 of the voters wanted candidate A to be ranked first, candidate B to be ranked third, right? Candidate C to be ranked second, and candidate D to be ranked last. Okay, so very simple, all the permutations. And in fact, distributions over permutations come up in a variety of applications. There's this voting application, but it comes up in preference analysis where you want to, say, rank your favorite foods, or maybe decide which books someone's likely to purchase, for example. It even comes up in multi-target tracking, where you're maybe in a security application where you're trying to keep track of who's inside a room, where they're walking. Or in a biological study, you're trying to study the behavior of ants, for example. Okay? And one common challenge of all of these applications is that as the number of things that you're tracking, as the number of things that you're ranking grows as n, then the number of permutations grows as n factorial. And just to give you an idea, when n is 9, it's not too bad. To store n factorial doubles, 9 factorial doubles, you need 3 megabytes. But if you just put that up a little bit to n equals 15, then all of a sudden you're talking about 2,000 petabytes just to represent that many doubles. Okay, so it's way too much. And this is a big problem. I'm going to call this problem number 1, the representation problem. And this is problem of how do we efficiently or compactly represent a distribution over permutations. And I'll put this icon of a hard drive to remind you throughout the talk of this representation or storage problem. I want to talk about one very simple way that people have done in the past to compactly represent these distributions. Yes?
So when you say way too large, what kind of scale are you looking at? If you have n objects, are you looking at linear, sublinear?
Linear n, you mean?
In the bits. If you have, well, I'm trying to get an idea of what way too large is from an order.
Oh, well, in that slide, I'm talking about way too large for the number of hard drives that my advisor would buy me, for example. But in fact, the problem is not just a storage problem. This is related to the sample complexity problem too. How many samples do you need to estimate all the probabilities? And in fact, that way too large comes a lot earlier than the storage complexity problem. But this is easier to talk about in some sense. So let me talk about this method. This is called the first order summary. Very simple idea. We're going to go through every candidate J and every rank I, and we're just going to keep the marginal probability that J was ranked in position I. For example, I did this for all 14 candidates of the 2002 election, and you can see that 25% of voters wanted to rank Sinn Féin in last place. Turns out if you go up this column, you can see that 10% of voters wanted to rank Sinn Féin in first place. So it's kind of a polarizing candidate in that election, which seems fairly typical of Sinn Féin candidates, actually, in Irish elections. That's not the main story. The main story here is that instead of n factorial numbers, all we needed to do was write down n squared numbers to, in some sense, convey the main features of this distribution. Okay? Of course, the first order summary is somewhat coarse. It doesn't represent certain probabilities. For example, we can't represent the joint probability that Sinn Féin is first and Fianna Fáil is second in a particular ballot. Okay? So the main idea that I'm going to put forth in this talk is somewhat of a new approach to representing distributions over permutations. And it's based on this simple idea that functions or distributions over permutations can always be decomposed, split up into sums of simpler, easier to work with functions, which can be more compactly represented. I'm going to call that the additive decomposition, and I'll talk about the multiplicative decomposition, where we're going to do the same thing, except we're going to factor it into products of simpler functions. I just want to give an example of what I mean by additive decompositions for functions on the real line. If you've seen Fourier analysis before, then this will seem very familiar. Given a function f, we know that there's this beautiful mathematical theory that writes f as a weighted sum of sinusoidal basis functions, increasing from low frequency to high frequency. These numbers, these weights, are called the Fourier coefficients, and these sine waves are the Fourier basis functions. We also know that if we drop some of these high frequency terms, it's often the case that we can get a pretty decent approximation to f if f was a pretty smooth signal. Okay? And so an idea for approximating f, or getting at the main features of f, is instead of representing all of these frequency responses, all of these Fourier coefficients, we can just represent the low order ones, the low frequency ones in purple here. That's one idea. Now it turns out more recently mathematicians have studied Fourier analysis for permutations, for functions or distributions over permutations. And if you've never seen something like this before for permutations, then the most surprising thing is that Fourier coefficients are matrix valued. And not only are they matrix valued, they're matrices of different sizes. And here's just one example for permutations for 5 elements, increasing again from low frequency to high frequency. I just want to give an idea of what frequency means for permutations. If we take the collection of all of the coefficients, if we know all of them, then it turns out it's possible to reconstruct all n factorial original probabilities using what's known as the inverse Fourier transform. Okay? It turns out if we drop all but the first 2 blocks, the 2 lowest frequency blocks, then it's possible to reconstruct all first order probabilities all the first order probabilities I told you about earlier in the talk. Does anyone have any guesses, by the way, as to what we get if we have the first 3 blocks?
Second order.
Second order. Good. Of all the times I've given this talk, you're the first person to answer that correctly. Yes. We can reconstruct all second order probabilities with first 3 matrices. And just to give you an example on the Irish data, so the second order is the probability or joint probabilities of pairs of candidates mapping to pairs of ranks. Here we see, for example, that 7% of the voters that year wanted to place the 2 of the phenol candidates consecutively in ranks 1 and 2. And this was something that was not captured by the first order marginals. And so, it's more detail, but at the price of more storage. And in this case, we need to represent O of n to the 4th marginal probabilities. Make sense? We can go on. We can talk about, we talked about second order. We can go on to third order, fourth order. And every time we go up, we have to store more numbers, of course. But if we fix an order, then we can represent low order marginal probabilities with polynomial Fourier coefficients, which is a nice thing. And in this way, the Fourier the Fourier approximations generalize the first order summary that I told you about before. And this is the first insight into solving problem number 1, this problem of representation, which is that using these low frequency Fourier approximations, which is equivalent to storing low order probabilities, we can get a good approximation and do it in polynomial space. Yes?
Just to make sure I understand that right, what you call a low order probability, is that a low, a moment of distribution, like a first, second, third moment? Or?
In some sense, yeah, it's like a moment. You can think of, it's not exactly a variance because we're not on the real line, but it's somehow they're probabilities that involve many objects at once. So if you have a graphical model, for example, you can think of cliques of size 2 and then cliques of size 3, and you're increasing the complexity of the marginals. As I go on, by the way, I'm going to organize my thoughts into this chart. We had this representation problem, and I told you about the additive or Fourier decomposition. The additive means that you're decomposing into a sum of basis functions. Now that we can represent a distribution, we'd like to answer questions about it. That's the inference problem. Just to give you an idea, for example, in voting, we might want to know, well, what are the odds that someone's going to rank Sinn Fein first, given that he ranked Fianna Fáil second? That's typically a very low probability. We might want to know if a voter ranks Labour first, is he more likely to rank Fine Gael over Fianna Fáil? And if you're into Netflix or watching movies, then you might want to know, well, if I prefer Titanic to Star Wars, then am I likely to also prefer English Patient to Jurassic Park? Something like that. In all of these problems, we need to solve Bayes' rule. We need to evaluate Bayes' rule, which is the posterior. We want to find the posterior probability given some observation z. Z might be, for example, that Fianna Fáil was ranked second. Bayes' rule tells us that the posterior is the pointwise product of the likelihood function and the prior distribution. Okay, and so here I'm just writing out both of these functions. They're both functions over permutations. And what I would do to do Bayes' rule is just go one by one through these permutations, multiply them, and get the posterior distribution. That's a O of n factorial complexity operation. And so our second main problem, problem number 2, is how are we going to efficiently compute a posterior distribution based on the new observations, Okay, and instead of a hard drive, I'm going to flash this little picture of Reverend Bayes, our good friend Reverend Bayes. And I told you about these Fourier representations. What we'd really like to do is do inference using these Fourier representations. Here's the problem statement. Given the Fourier blocks, the first low frequency Fourier blocks of the prior and low frequency blocks of the likelihood, we'd like to somehow end up with low frequency blocks of the posterior distribution without having to reconstruct our approximations and then go through one by one and multiplying all the probabilities. The insight that we use is very simple. It's It's based on the fact that pointwise products correspond to convolutions of Fourier coefficients. And this is a pretty well-known fact from signal processing. There were two complications for us. One was that no one had ever actually tried this for permutations. And it turns out it's because this fact doesn't exactly hold for permutations. The complication is that no one knows how to convolve matrix-valued functions where the matrices are different sizes. So we kind of struggled with this for a little while. The answer, it turns out, is to use the Kronecker product to multiply these matrices. So let me just show you what the algorithm looks like. Convolution looks like polynomial multiplication. So we have this prior, the Fourier blocks of the likelihood. Just like polynomial multiplication, you multiply every pair from each factor here. And you multiply using Kronecker products. Then there's a projection to the Fourier domain, which unfortunately I can't go into details about. And finally, we add up all of the like terms, just like polynomial multiplication. And that gives us a representation of the posterior distribution. Our algorithm is quite general. It works for any prior, any likelihood on the symmetric group, on the group of permutations. And in fact, we can show that it works for functions over arbitrary finite groups. And in fact, arbitrary compact Lie groups, if you're familiar with group theory. Okay, so it's quite general. Unfortunately, sometimes when you do conditioning using this Kronecker update thing, you sometimes end up with higher order, higher frequency terms than the ones you started off with. This is because of the way that convolution smears information from low frequency to high frequency. What you can do is very simple. You can just drop the higher order terms that you don't want, or just not compute them in the first place. And that's called band limiting. That's an approximation. What we can show, though, is that if you started off with high enough order terms of the prior distribution, then certain low order terms of the posterior can be reconstructed after conditioning exactly. I won't read this theorem, but let me just give an example. If we start off with third order knowledge of the prior distribution and make an observation about one single object, maybe you see that Jurassic Park was ranked first, then we can infer the second order coefficients of the posterior distribution exactly after conditioning using our algorithm. Okay?
So John, in the illustration, the matrices, the size is increasing and then it's decreasing. And I'm confused because normally it should go to n to the power n, right? So there's redundancy in the marginals. Yeah. The first order of redundancy is that for example, in the first order marginals, you have to sum to 1 across the rows and the columns. Mm-hmm. When you start talking about pairwise marginals, you get you start talking about symmetry. So the probability that ij maps to kl has to be the same probability that ji maps to lk. Mm-hmm. And then there's also when you marginalize along one variable and then you have another. So these are local consistency rules. All these rules enforce a lot of redundancy. What the Fourier transform does is it represents the free parameters such that there's no redundancy along these. Somehow when I put these together and then I use a magical formula that I'm not talking about to, I can reconstruct the marginals. Okay. But these represent exactly the free parameters.
So I'm getting a little bit lost like in the specifics of this. These varying size matrix functions are very central, I think. Can you give like a little example for three, let's say, the permutation with 3 things? Mm-hmm. How such a matrix function would look like?
How such a matrix?
These matrix functions that represent.
Yeah. I don't know if I can use this board if they'll be able to see me, but if it's okay.
We're here.
Okay, great.
Priority.
I'll just show for the first order marginals. So one possible first order marginal would be, for example, you have half probability of, so these are your candidates 1, 2, and 3, and these are your ranks 1, 2, and 3. Mm-hmm. Maybe A, B, and C is better. And you can have a first order marginal of mapping to something. And the constraint is that down these columns, it has to sum to 1. So this would be 1/2, and this would be 0, and this would be, I guess, 3/4. And also along the rows, it has to sum to 1. Because of this redundancy, there's really only 5 free parameters specifying a doubly stochastic matrix. The fact that, so in fact 4 if you constrain it to sum to 1, but this summing to 1 is one of the parameters, what it sums to. So the this number right here tells you what all the rows and columns sums to. That's the normalization constant. You can think of it as the DC component of your signal. Those 4 numbers specify the numbers that, how will I say? So not those numbers. The next block is going to be a matrix of size 2 by 2. Okay? And they somehow represent what happens if you fix 4 numbers in this matrix. Once you fix 4 numbers, the rest is determined. And geometrically, what these numbers mean, it turns out if you take, so this is permutations of 3, it's geometrically, so if you take this triangle, these 4 numbers represent the rotation matrices that flip the triangle onto itself to permute these 3 points. So that's what the Fourier coefficient does. It's kind of abstract, and it's hard to explain when it's larger than 3, unfortunately, because then you have to start thinking about.
So these matrices are constraint matrices. They're doubly stochastic matrices.
No. So those Fourier blocks are not doubly stochastic. It's that I can represent doubly stochastic matrices by taking those numbers and making this triangle in some sense, and then trying to compute what's the probability that one vertex will map to another vertex.
So it sounds like what you're saying is that each matrix is representing the additional degrees of freedom to get the next order.
Exactly, yeah.
Okay. Okay, no, that helps a lot. Thanks again.
Sure. I apologize if that wasn't clear, but yes, you can ask me offline if you want to. Okay, so I talked about band limiting, and unfortunately, you do get band limiting errors, and one weird thing that can happen is that it can lead to approximations that make no probabilistic sense. You might even get negative probabilities in some of these approximations, which is bad. And despite what our friend M.C. Escher might have you believe about the impossible, these negative probabilities cause us to make really bad inferences sometimes. And we'd like to have some mathematically principled way for dealing with these negative probabilities. One way to view this is we have this space of all the possible Fourier coefficient matrices. And then within that space, we have a polytope, in fact, of Fourier coefficient matrices that correspond to some true or valid probability distribution. Sometimes band limiting lands us outside this space. And so one way we deal with this is to simply project it back in. We find the closest point in this polytope to the infeasible approximation. We were able to show a few years ago that this is possible to formulate as a quadratic program. And so this projection can actually be done pretty efficiently. Okay? And it turns out to make a huge deal in practice. I'll show you some experiments shortly.
So you're always going to be projecting onto the surface of this feasible region?
Yes.
So have you been able to use that fact to help at all with either doing the projection itself or the inferences that you're going to make from that? Because presumably, I mean, if you could end up with any set of coefficients, you're going to be most likely to be outside the feasible region. So your projections, are going to be always on the surface of this feasible region.
Mm.
And so, we're going to be spending most of the time on the surface of these.
No, it's not always the case that you spend all your time on the surface of the feasible region.
Cool.
Often it doesn't land you outside that region. Sometimes it does, and when it does, you have to project yourself in. And the other bit, as I would say that so for example, you can imagine that maybe just a few of the coefficients are the troublemakers, and so this will project them back in somehow. And it has to modify the other coefficients to make this okay, but but somehow it works out.
It's sort of, in practice, it doesn't happen very often, and when it does, it sort of is a local shift.
Well, it's problem dependent, so I can't say that it just doesn't happen that much, but it depends on the problem.
Sure.
Sometimes it doesn't happen too much.
Yeah.
And I'll tell you more about how that works. Okay, so I want to give some examples for tracking, and this is highly important problem, comes up in video analysis and assisted living monitoring, which is one of the ways in which I got involved in this project. The problem here is we have some identities and we'd like to match them up with tracks along which they're walking. And so just to give you a cartoon example of what's going on here, we have these 4 people, they're walking along tracks, and sometimes the tracks get close together, and so we confuse who went where. For example, we have 3 what we call mixing events in this trajectory, in this joint trajectory, I guess. And sometimes someone walks close to a camera. Maybe you see their face, okay? And when that happens, we can tell who was at that track, maybe with some probability. And we want to use that information to infer, well, maybe who is at some other track, or where is some other person. Can anyone see, by the way, where this girl is?
Are they right on the sides?
She's on the right hand side.
Where you put them?
They have to be on the sides.
Isn't she just there? Yeah.
She's on the right, but in particular, she's at the bottom here. And the reason why is because she came down here, but we know she couldn't have come up here because this guy came down here. So that's the inference problem, okay? And this is a combinatorial problem to do this reasoning, and it's in fact Sharpie complete to do this. This is some simulated results on a hidden Markov model with this problem. And here's the approximation by a uniform distribution to the posterior distributions, the true posterior distributions. This is just a small problem. Unfortunately, if you do the Fourier analysis without projecting, this is just one problem where the projection did make a big difference. Sometimes it doesn't. You get really big errors. After projection, you typically get much lower errors. And what's natural is you see that you do okay with first order, you do slightly better with second order, and you do slightly better with third order. And if you keep on going, then you'll get even smaller.
So what was the error? Like,
how do we compute the errors here?
Yeah.
This is we're taking the true first order marginals. So we're able to do the updates exactly in this case because it's only six items. And we're comparing the L1 distance for the posterior marginals.
The other thing you could have done is basically compute the map under this distribution.
Yes, and in fact, I'll show you that in the next slide on a different problem. Here, what we're doing is we're tracking 11 individuals walking around in a lab environment. The computer vision here is, I would say, not very sophisticated. We're just using color histograms to gauge who is where. This is the performance of what we call an omniscient tracker. He's not really omniscient. He needs to still deal with computer vision in spite of all of these conclusions and stuff. But he does know the result of every mixing event when people get too close together from hand-labeled ground truth. This is the performance of time-independent classification. So we're not using prior and posterior. We're not using Bayesian inference of any kind. We're just looking at a single frame and doing a classification based on color histograms. Here's the performance without projection, and here's our performance with projection. Here, we're just using second-order marginals, or second-order Fourier terms. Okay? And you can see it's doing almost as well as omniscient tracking. In this problem, we can see that the projection was crucial. And these are, so I just want to summarize the inference problem again. We're able to formulate inference as this generalized kind of convolution with Kronecker products, and low-order observations typically correspond to polytime or more accurate inference.
Is that Ashish in the video?
No, this is taken at Stanford, actually. Okay. So there are a bunch of grad students in a basement in the Packard building there. Okay, that's inference. I want to move on to the next decomposition. Sure.
So how scalable is this? So for example, these representation matrices,
Uh-huh.
how big do these get for sort of...
That's a great question.
15 or...
And I'm going to talk about that now. This is the scaling time of exact inference. You can see that it just blows up. This is factorials. The cost of inference is n factorial squared in this case, exact inference. This is the Fourier analysis version. You can see it scales much more gracefully. But what this plot hides is how high these lines will go. This is just for n equals 8. And in fact, we can just go up to maybe n equals 30. At most, n equals 40 if we're willing to wait for a really long time. The reason why is because polynomial is just too slow sometimes, right? At third order, you're representing n to the 6 Fourier coefficients, right? And this is not even counting the cost of inference. And so it's quite costly. And after doing this project, we had to go back and reevaluate, well, is it possible to achieve more compact representation, maybe taking account of other structure? This is an idea that we've recently been working with. Here's the idea. We're going to assume that a ranking or a permutation is created by shuffling smaller independently drawn permutations. So just as an example, let's imagine ranking a set of fruits and a set of vegetables, okay, by preference, what you like. You might decide to rank them separately first. So maybe you like artichoke better than broccoli. Maybe you like cherries better than dates. Then in our model, what we do is we assume that you have a next step of selecting a shuffling of these. So maybe you like vegetables, all the vegetables better than all the fruits. But it could be any one of the other possible interleavings of the vegetables and fruits. And finally, what we do is we fill in these rankings down here in the joint ranking. So if you like artichoke better than broccoli, then down here in the joint ranking, you like artichoke better than broccoli. Okay? It's very simple, and when fruits and vegetables are drawn this way, we say that they're riffled independents. And this is named after probably the most popular style of card shuffling, the riffle shuffle. And what I hope to claim to you over the next few slides is that riffle independent distributions can be represented using much fewer parameters, very few parameters. Okay? Now, despite the fact that this was inspired by card shuffling, we've been able to find it in real data, surprisingly. Here's a data set from the American Psychological Association. They elect their presidents using this ranking style ballot. In the 1980 election, there were 5 candidates. It's a pretty small data set, but we have access to about 6,000 votes. Since there are 5 candidates, there are 5 factorial or 120 possible ways to rank those 5 guys. Here are those 120 permutations, and gray shows how many people voted for a particular permutation. A natural question to ask for this data is whether there exists some riffle independent distribution that approximates this gray line well. The answer is yes. This blue line. And this blue line comes from when you assume that candidate 2 is riffle independent of candidates 1, 3, 4, and 5. The interpretation of this is pretty interesting. It's that candidate 2, what people preferred about candidate 2 was completely independent of how they preferred the remaining candidates in that ballot. Okay? Relatively prefer those remaining candidates. I promise you that riffled independence would save you some space. So let's just count up the parameters. We need to first rank the vegetables, right? That's candidates 1, 3, 4, and 5. So there's 4 factorial ways to do that, 24. Then we need to rank the fruits. That's candidate 2. There's 1 way to do that. And then we need to interleave candidate 2 with the remaining candidates. 5 ways to do that. If we sum this up, we see that the number of parameters required to specify this model is no more than 30. But you might look at this 4 factorial and you say, well, that's a distribution over permutations as well. Maybe we can make further riffle independence assumptions. And so let's just see what happens if you split this group up. We can imagine splitting it up into these 2 smaller groups. And in that case, you can count the parameters again. I won't go into the details, but if you sum up these numbers, you'll see that at most we need 16 parameters to represent a model over distributions over permutation using which would ordinarily require 120 parameters. Okay? And so this is our second insight into representation, which is that Riffle-independent distributions, especially ones that factor hierarchically, like the one that I just showed, can be represented, in fact, using exponentially fewer parameters in general. I want to talk a little bit about what these hierarchies mean intuitively. So let's go back to our fruits and vegetables. You might rank your fruits first, again. Bananas better than apples or something. Then you rank your vegetables, carrots better than broccoli. Then you interleave. That's one layer of the hierarchy. At a second layer of the hierarchy, you might have extra foods. You might have cookies and candy cane. And so the hierarchy just tells you to interleave the junk food back into this kind of healthy set of foods. So you might do something like this. At the end of the day, you like maybe candy better than broccoli, okay? So it's good. These models are very intuitive. They're very simple. One problem that prevents us from working with these hierarchies directly is that typically you won't have access to what hierarchy generated your data. Okay? Now with the fruits and vegetables, you might be able to guess what that hierarchy is. But if you look at the APA data, those candidates, if you didn't know about the politics of the American Psychological Association, you might not know what hierarchy to use. And so our solution is a machine learning one. It's to use the structure that best explains the data that we have. Here's the cartoon. We have some cloud of rankings. The goal is to discover or design a structure learning algorithm that finds the hierarchy that best explains the Riffle independence relationships within the data. Now, if you're familiar with graphical model structure learning, there are a lot of things that can go into such an algorithm. But at its core, for us anyway, we have to solve the following problem. Given a set of IID ranked data, we'd like to determine whether two subsets of items are Riffle independent of each other. Okay? Here's the insight that it's based on, that we use. It's very simple. The idea is that absolute rankings of fruits, if they're Riffle independent of vegetables, are not informative about relative rankings of vegetables. So for example, if I tell you my preference over fruit I, then that should tell you nothing about my preference of whether vegetable J is better than vegetable K. Okay? This is just for 3 items at a time. And for example, one way to measure this is using mutual information. If I lies on one side of the split, J and K lie on the other side, and I measure this mutual information, then that better be 0 if the fruits and vegetables are Riffle independent. This is just for triplets, like I said, but we can extend this to subsets of items where we're summing over the triplets that cross between 2 sets. For example, this triplet that straddles the sets A and B, if A and B are, this triplet that straddles A and B adds a penalty to an objective function which measures the Riffle independence of A and B. Because if A and B are Riffle independent of each other, that triplet better be 0. On the other hand, something inside here, inside of A, does not contribute to the objective function. The learning problem is to minimize this objective function with respect to subsets A and B. And there's exponentially many subsets that you can search over. And unfortunately, I won't be able to go into the details, but we've been able to design an efficient minimization algorithm that works with high probability in this case. So I want to jump into examples. Here's again the APA data. This is the tree that we learned when we used our algorithm. And you can see that it partitions off candidate 2, just like we thought before. And then it partitions into 1, 3, and 4, 5. And in fact, in this tree, you only need 11 parameters to represent that distribution. Here are the candidates again. And what's interesting about the APA is if you look into the politics of these elections, you'll notice there's 3 groups that kind of fight for control of the APA. There's the research psychologists. These are the academics. There's the clinical psychologists. They're the practitioners in some sense. And then there's what's called the community psychologists. These are the research guys. These are the clinicians and the community psychologists. And it's perfectly reflected by the hierarchy, even though we told the algorithm nothing about the politics beforehand. Okay? So that's a nice result.
Is researcher to a female?
No, it's a male. I think he might even have a Wikipedia page. I'm not sure. I definitely been to his webpage, though. I saw his picture. Very old male. Here's the first order marginals. Here are the true first order marginals that are estimated from just histogramming the data. And here are the hierarchical first order marginals from our approximation. And you can see the two matrices are quite similar. Here's the performance of our algorithm on synthetic data, where we know that there is a true hierarchy that generated the data. What I'm doing here is I'm giving the algorithm the knowledge of the true structure, and it only needs to learn parameters. As I increase the sample size, it gets better and better, naturally. Here's an algorithm that uses the wrong structure. It happens to generalize another model that was proposed a few years ago. And since it has the wrong structure, it still increases in performance, but there's this gap. Here's our algorithm that is allowed to learn structure as it goes along. And in fact, at the end here, it's learning the same structure almost every time as the true structure. We can show that happens with high probability, actually. So we have a sample complexity bound, which says that with high probability, we only need polynomial samples to learn the true structure. Okay. Here's the Irish data again. I showed you these first order marginals earlier. The first thing we did here was we decided to try to guess at the hierarchy without learning it. And the hierarchy that I guessed was, well, maybe major parties are Riffled independent of the minor parties. That was my guess. Here's the first order marginals of that approximation. You can see it's actually not too bad. You need to stare a little bit carefully, but this blob is sort of here, and you can see this blob is on the other side. The main thing that's missing is this bright white patch in the middle, or on the bottom here. And these two columns correspond to Sinn Féin and Christian Solidarity parties. And in fact, if you think about it, the Sinn Féin and Christian Solidarity parties are sort of somewhat outliers in Irish politics. And so one thing we were thinking, well, maybe if we had removed those two parties from the election, we would have gotten better approximation results. This is what happens when we run structure learning on that data set. It first removes Sinn Féin, then it removes Christian Solidarity, and it's left with the remaining candidates. Following that, it removes the Fianna Fáil candidates, all three of them as a chunk. It removes the Fianna Gael candidates, and we're left with all the independent candidates and two of the minor parties. Okay. Since there's 14 candidates, we can do a kind of a brute force optimization of the objective function. That takes 70 seconds. Our algorithm takes 2.3 seconds, which is much faster. If you were to represent explicitly a distribution over 4 factorial permutations, it would take 87 billion numbers, but this model requires 1,000 numbers. Okay. And here again are the first order marginals. So here's the true marginals. Here's our learned first order marginals. And in this case, it's a little bit hard to see, but in this case, it looks quite a bit nicer. Let me turn to preferences. Here's 5,000 preference rankings of 10 types of sushi taken from a professor in Japan. These are the types of sushi. Here's the first order marginals from that data set. Let me just point out some of the main features of this matrix. Fatty tuna is seemingly everyone's favorite in Japan. And unfortunately, no one likes cucumber roll. Poor cucumber roll. Here's our structure learning results. This was kind of surprising to me because I didn't think it would return anything meaningful. I didn't know that sushi had political parties, for example, but they do. Here's the tuna political party: tuna, fatty tuna, and tuna roll. Then we have egg and cucumber roll on this side. So these are the vegetarian options in some sense. And this one's kind of interesting. It's sea urchin and salmon roe. We thought, well, maybe this is a more exotic type of sushi, but different people have different opinions. So Ui Tae was telling me that he thought it was the sushi here that had no meat. They're kind of the non-meat but non-vegetarian choices. So up for interpretation. Okay, good. So I told you about hierarchical riffle-independent models. They're very expressive, and we can do structure learning with them in polynomial time, polynomial samples too. I want to compare the two representations a little bit. We have additive decompositions on the one hand that can represent low-order effects pretty well, but they sometimes require too much storage, despite being polynomial in size. On the other side, we have multiplicative decompositions, which, while they can typically be represented with very few parameters, they make these aggressive independence assumptions about the data. And if your data doesn't have those, then it's not such a good approximation. One question that we asked was whether it's possible to get the best of both worlds somehow. And the answer is yes. What we did was an adaptive approach where we used the Fourier decomposition on subsets of items that were more strongly interacting. And we used the multiplicative decomposition for subsets of items that were more weakly interacting with each other. And due to time, I won't be able to go into details about this approach, but I just want to show some examples on this ant tracking data set from Georgia Tech. This is the scaling of this tracking problem as you increase the number of ants from 20 to 100 of the adaptive algorithm. And you can see that we scale quite gracefully, almost linearly, I would say. And here's the scaling behavior of the non-adaptive algorithm, which we weren't able to run on 40 on this particular example. This is the accuracy, the tracking accuracy of the two methods, just to compare. This is the behavior of the non-adaptive algorithm. Here we're varying the problem setting. So we're giving we're hiding certain observations from the algorithm. And as we increase the number of observations that it gets to do better and better. And here's the performance of the adaptive algorithm. Sorry that it's kind of dark and hard to see. The main feature of this is that the adaptive algorithm does better and better, and it catches up with non-adaptive quite quickly.
So just to be clear, this is identity tracking.
This is identity tracking. Yeah, this is not a ranking problem. Okay, so
just quickly, those ants don't seem to have identities.
No, they don't. So that was a simulated part of this problem. We gave them identities.
You gave them identities at the beginning and gave them the identities at the end, and it had to work out what happened in between.
Yeah. So the only I would say the realistic part of this problem is the movement patterns in the data.
Okay.
Some labs, by the way, actually, when they do these problems, they paint the ants little colors, and there's still the tracking problems because some of the ants go into holes and you lose track of them, and so there's still a problem there. But I haven't been able to get that data. So good. So this is the red box that I've used to show that we can actually use both decompositions in tandem. And with the time that I have left, I'm going to talk about how to do inference using these multiplicative decompositions, which is my newest work. Just to set the scene a little bit, I want to talk about top K inference. It can take a long time to go through 14 candidates and decide who do you like first and who do you like second, all the way through who do you like 14th. More easy is to just report your top K favorite candidates. And this is exactly what this guy is doing. Okay, so 1, 2, 3, 4, just the top 4 choices. And in fact, if you look at the data, by and large, people just put down their top 3 or top 4 choices for candidates in Irish elections. Okay? And because people behave this way in these elections, a common question that comes up is the following. Given an observation of the voters' top K rankings, how do we predict or how do we infer his preferences over the remaining n minus k candidates? This is Bayes' rule again. I told you about that earlier. It's an O of n factorial operation. And I did tell you that with Fourier decompositions, we can handle low-order likelihoods, observations that depend only on a few items at a time in polynomial time. We want to ask the same question about riffle-independent decompositions, whether it's possible to do efficient inference. And what I want to convince you of is that the answer is yes, it is indeed possible to do efficient inference. And it's possible precisely when the observations take a particular form, when they take the form of what we call partial rankings. And so as a corollary of this, we're going to be able to condition on the top k observations very efficiently for Riffle-independent models. So I just want to give a quick example of how this would work if you're conditioning on top 1. Okay, so someone tells you someone tells you that candidate 3 was their favorite candidate. Now, if you knew that candidate 3 was from the phenol party, then you can break this observation into 2 smaller observations. One is just on the phenol candidates, that candidate 3 was ranked first among phenol candidates. Okay? This observation also tells you that something about the interleaving. It tells you that there was some phenol candidate that was ranked first overall. Okay? And using this decomposition of the observation, in fact, instead of going through one by one and conditioning every single permutation, what we can do is we can condition each of the parameter distributions independently of each other using this decomposed observation. And so as a result, we are able to get linear time conditioning, linear in the number of parameters of the model. Now, I just showed you this for a one-layer hierarchy, right? But in general, for arbitrary hierarchies, top 1 inference problems decompose into inference problems at each node of your Riffle-independent hierarchy. And so that's quite nice. Going beyond top 1 inference, we have what we call partial rankings, where items are allowed to be tied together. For example, in what we call approval votes, you're allowed to check some subset of candidates that you approve of. The guys with checks are tied. The guys without checks are tied behind the guys with checks. There's these partial rankings are all the rankings where any subset of items are allowed to be tied. And what we were able to show is quite a general result, which is that any partial ranking observation decomposes in the same way that I showed you in the last slide, decomposes into smaller conditioning problems on each node of the hierarchy, thus allowing us to condition in linear time.
So in this particular case, just a classification problem, right? There's no ordering between pluses, so I call them...
No, there's still...
What ordering is there remaining other than between the group of pluses, crosses, and the group of non-crosses?
So you view this as someone does have a permutation in their mind, but they report to you a censored version of that permutation. However, there's still a permutation there, and over many people, I might have a twin who might just check off phenol and Sinn Fein. And so over this, it induces a distribution over permutations. Now, sometimes the distribution isn't identifiable from this kind of information, but we might just want to, one question that you might want to solve is, what's the probability that you like drama movies over action movies? And this would be a question that you can answer in this framework. Okay, so we were pretty excited by this result. It's very general. Partial rankings cover a lot of ground. And we wanted to know, well, what other observations could we decompose in this way? And in fact, we spent several months, this is Ashish and I, we spent several months thinking about what other observations could we handle using this decomposition. We could never come up with any examples. And in the end, we found out that this was impossible. What we were able to show in particular is that partial rankings are in fact the only decomposable observations. Yes?
So are all partial orderings in partial rankings?
No, partial rankings are a subset of partial orderings.
Okay.
Yeah. Yeah, you can think of them as censored linear orderings. Okay. So it's but larger than full orderings, but smaller than partial orderings.
But did you think about partial orderings?
Partial orderings, in fact, are, you can show that it's Sharpe complete to condition exactly on them.
I think you should wrap up soon.
Okay, and I will. Let me just show some results. So before we could handle partial rankings, we could only use the full rankings in the Irish data set. And this is the model quality that we get from learning just from the full rankings. That causes us to lose out on a lot of the data. Okay, in fact, there are 60,000 incomplete rankings, but only roughly 3,000 full rankings in that data. Here's what happens when we use everything in that data. And so it increases the model quality when we learn. And just for reference, this is the performance of a competing model. I would call it the state-of-the-art models in using partial rankings by Guy Lebanon and his student Yi Mao. And you can see that at least on this data set, we're doing either as well or somewhat better than them with much fewer parameters. Okay? And so using this top K inference, we're able to build more accurate, very interpretable models using partial ranking data. All right. So I'm actually going to skip over the future work because we're out of time. We can talk about that in our meetings. But let me just wrap up. I talked about these two problems that I'm interested in. Representing distributions. I'm in general interested in representing distributions over combinatorial structures such as rankings. And there's this twin problem that comes with it, which is how to do efficient inference once you have these efficient representations. And I gave some ideas based on additive decompositions and multiplicative decompositions for this problem. And there's a bunch of applications that I'm excited about, and as well as future work, which I didn't get to talk about. Thank you very much.
Very nice talk.
Thanks.
In your examples and in everything of the representation and inference, you have always assumed that each item has a unique ID. But in many applications, you might have some observations, and you can learn a model from them. But afterwards, at test time, you might have different observations. You still only have some information for each item that allows you to transfer preference. For example, web page data. I saw it on the last slide you skipped over. Is it applicable to these kind of problems, learning to rank problems? Or
yeah.
Not?
So I think more to make in a lot of ranking problems we have features that we can generalize from. So it could be well, in the candidates it could be their political leanings, whether they're left or right, or what region in Ireland they're from. It doesn't have to be just Ireland, of course. And using those features, I think we can. I didn't use them in what I talked about, but we are interested in using those features in these models.
All right, one more. Yes?
Nice talk.
Thank you.
I have a potentially vague question. So you said Reverend Bates is your friend, and I was wondering about, can you give us an intuition for what it means in terms of the prior, when you discard the quote-unquote higher order frequency coefficients?
I think there's different ways to interpret it. One is that I'm just not telling you about the higher order terms. And so, for example, in the tracking problem, I know that Alice is likely to be at a particular track in the prior, from what I saw in the last few time steps. That would be my prior. But in the second order, if I told you the second order terms, I would know that Alice is, hopelessly in love with Bob. So they always walk in adjacent tracks, and that's not something that would be captured by a second. Without a second order information prior. Something like that.
All right, I think we